This lecture deals with measures of association for interval ratio variables. Topics include scatter plots, covariance, and the coefficient of correlation. A common starting point in examining the association between two interval ratio variables involves using something called a scatter diagram, also known as a scatter plot. A scatter plot is a graph that graphs the values of the variables against each other. Typically, in a scatter plot, the values of the independent variable are plotted on the horizontal, or x-axis, and the values of the dependent variable are plotted on the vertical, or y-axis. Points on the graph mark the intersection of the independent and the dependent variable. As an example, consider the association between education and father's education for a sample of 10 cases from the General Social Survey. And here we'll see education and father's education graphed on an interval ratio scale. So here's our data set, including 10 cases for father's education and respondent's education. Let's take a look at some of these values. Let's take a look at the values for the first case. We notice that this person has 16 years of education, and we notice that that person has 12 years of education for their father. If we were to graph all 10 of these cases in a scatter diagram, it would look something like this. So notice that the values of the independent variable, in this case father's education, are arrayed along the horizontal, or x-axis, and then values of the dependent variable, the respondent's education, are arrayed along the y, or vertical axis. Each of these points represents the location on both of these variables for all the individuals in our data set. For example, this point marks the location of case 1, and you'll recall that case 1 had 16 years of education and 12 years of father's education. Likewise, we plotted all 10 points on their relative location of education and father's education. Now, what's the overall pattern here? Well, you can see that there seems to be a tendency for education to increase along with father's education. In other words, as we go from low values of father's education to high values of father's education, we're also going from low values of education to high values of education. And that means that there's a positive association here. Note that we could also locate the mathematical or arithmetic center of the data. And that's the point where the average of both variables meets. And so here we see that the average of respondent's education is 14 years, while the average of father's education is 12.2 years. This point, which marks the intersection of those two values, marks the arithmetic or mathematical center of the data, something called a centroid. We'll use the centroid later in the calculation of the covariance, so keep it in mind for later. So, recall that in a previous lecture we used variance as a measure of variability for interval ratio variables. Well, it turns out that there's a related measure, something called covariance, that's used to measure the association of interval ratio variables. Before we talk about covariance, let's review variance quickly. Recall that it measures the average distance of each score in a distribution from some center point. That is, the average deviation from the mean squared. Here's the formula for the variance. Remember that in the numerator, we had the sum of the square deviations from the mean, in this case for some variable y, divided by n minus 1, where n stands for the sample size. So, let's suppose we wanted to calculate the variance for the variable education for our sample of 10 cases. That involves taking the average, which in this case is 14, and subtracting it from every category of the variable for each 10 of the cases. And so the first case has 16 years of education. 16 minus 14 gives us 2. The next case has 15 years of education. 15 minus 14 gives us 1. The next case has 0 years of education. So 0 minus 14 gives us negative 14. And so on. We do this for every case. Notice that when we add them all together, the sum of the deviations equals 0. And so we have to do something to exaggerate the difference so that they sum to something other than 0, so we can find the average deviation from the mean. And so we square it. And so for the first person, we've taken 2, the deviation from the mean education, and squared it, and we get 4. The second person had only a 1-year deviation from the mean, so 1 squared is 1. The third person had negative 14 years of education, deviated from the mean. So when we square that, we get a positive 196, and so on. We do that for all 10 cases. And then we get the sum of the squared deviations by adding across the column, and we get a value of 276. When we divide that value by the number of cases, in this case 10, minus 1, or 9, we get a value of 30.67, so that's the variance. Now let's talk about covariance, which is a measure of linear association between two variables. Conceptually, it's very similar to the variance. The only difference is that we take the product of the deviations for two variables, and then we multiply them by each other. Think of it like taking the deviation from that center point, the centroid, that we saw in the scatter diagram earlier. Here's the formula for the covariance. In the numerator, we see that we have the deviations of the mean for one of the variables, x in this case, and the other variable, y. And what we do is we take the deviations for both of them, multiply them together, and then sum them. And then we divide that value by n minus 1. Let's take, what does the covariance tell us? Well, it can be either a negative or positive value indicating the direction of the association. The magnitude of the covariance tells us something about the strength of the association. That is, the further away it is from 0, the stronger the association. And the closer it is to 0, the weaker the association. And that's true if it's departing from 0 in either direction. So you can have a strong negative association, a weak positive association, or vice versa. Let's calculate the variance for the example of education and father's education, using our sample of 10 cases. Recall that the average for education is 14, and the average for father's education is 12.2. First, we do the same thing we just did in calculating the variance. That is, we take the deviations from the mean of the dependent variable, education. And so we've already done the work for this. But we also have to take the deviations from the mean for the other variable. So here what I've done is I've taken all the values of father's education for all 10 cases and subtracted the mean. Next, what we have to do is we have to multiply the deviations from the mean for both variables. And we have to do that for all 10 cases. That is, we have to get the cross products for the deviations. Let's look at that in slightly more detail. So, for the first person, that person had 16 years of education. Recall that the mean education was 14 years, so that person had a deviation of 2 years. That person also had a father who had 12 years of education. And recall that the father's education had an average of 12.2 years. And so when we take 12 and subtract the average, we get negative 0.2. Then what we do is we multiply those deviations by each other. So we'll take the 2 and multiply it by the negative 0.2, and we get a value of negative 0.4. We do that for all 10 cases. And then the next step is to take the sum of those cross products. That is, we're going to take the sum of the deviations from the mean of y multiplied by the deviations of the mean for x, that last column in our table. And we get a value of 149. And then we just divide that value by the total number of cases, in this case 10, minus 1, or 9. So when we divide 149 by 9, we get 16.55. So what do we learn about the relationship between father's education and response education from this value? Well, first of all, we see that it's a positive value, meaning that as father's education increases, so does the response education. Now, the magnitude of the effect is a little bit hard to tell because it relies on the underlying metrics of both variables. But we're going to learn another value, something called a unit-free measure, that's going to allow us to have a more easily interpretable metric to judge the strength of the relationship between the two values. And that measure is something called the correlation coefficient, which is also known as the Pearson's correlation coefficient. It's like the covariance, but it doesn't rely on the underlying units of the variables. That is, it doesn't depend on whether some variable is measured in years or in decades or what have you. Whatever the underlying unit that's being measured, this measure will give you some value that always ranges within a range of -1 to 1. So basically, you can think of the coefficient of correlation as a type of standardized covariance. Here's the formula for the coefficient of correlation. We use R to refer to the coefficient of correlation, and R is equal to the covariance of the two variables, here is represented as S sub yx, divided by the standard deviations of the variables, multiplied together. The coefficient of correlation indicates both the strength and the direction of the linear association of the two variables. It ranges from -1 to 1, -1 and 1 indicating, respectively, perfect positive and negative associations, and 0 indicates no association. Typically, the coefficient of correlation takes on intermediate values between -1 and 1. So, as an example of how to interpret the coefficient of correlation, take a look at this scatter diagram. This shows a scatter diagram for a randomly generated dataset of 50 cases in which we have a strong correlation. In this case, the R value is 0.90. Notice that there's a tight clustering of values along a line, which indicates that there's a very strong fit between these two variables. Here's a more moderate fit. Here is another randomly generated dataset of 50 cases in which the coefficient of correlation is only 0.48. Notice the more diffuse pattern of the relationship between the two variables. And then finally, here's a very weak association, a value of 0.606. So you can see that R, the coefficient of correlation, is basically measuring the extent to which two variables go together in some kind of a linear fashion. Okay, let's take a look at the example of the coefficient of correlation for education and father's education. So, in order to calculate the coefficient of correlation, we need two things. First, we need the covariance of the two variables. And remember that we calculated that to be 16.55. We also need the standard deviation of the two variables. And so we can get the standard deviation for education by taking the square root of the variance we calculated earlier. Remember that we calculated the variance to be 30.66, and it turns out that its square root is 5.53. We also need the standard deviation of the father's education, and we get that by taking its variance, which turns out to be 11.73, and taking its square root. So the square root of the variance for father's education turns out to be 3.42. And so to calculate the coefficient of correlation, or R, we're going to take the covariance, 16.55 in this case, and divide it by the product of the standard deviations of the two variables, 5.53 for the respondent's education and 3.42 for the father's education. We get a value of 0.87. So what does this tell us? Well, first of all, it tells us that there's a strong association, because this value is closer to 1 than it is to 0. It also tells us there's a positive association. In other words, as we increase the values of father's education, we're also increasing the values of respondent's education. However, we should be very careful in talking about correlation, because correlation doesn't equal causation. There are many other things that could be at work. Correlation could simply be the spurious result of some other variable that's causing both things, or the relationship may be simply epiphenomenal. As an example of this, consider the next slide, which shows the correlation between cheese consumption and the number of civil engineering PhDs, granted in a 9-year period between 2000 and 2009. Notice that there's a very strong relationship between the two. In this case, the coefficient of correlation is 0.96. But surely the number of PhDs awarded in civil engineering have nothing to do with the consumption of mozzarella cheese. So this happens to be a spurious correlation that's relating two factors that have nothing to do with each other. So again, correlation shows us how two things go together, but that doesn't mean that these things are causally related.